All right. So today we will be talking about phase diagrams. So they are the representation on a graph of the physical states of different molecules. And these physical states will change depending on three things. That will be the pressure, the temperature, and the intermolecular forces. On the graphs, though, and depending on the strength of the intermolecular forces, will give you whether you're in what state you're in at a given pressure temperature. So let's look at one of these phase diagrams, or not yet. Changes in state will occur when kinetic energy exceeds the strength of your intermolecular forces. So you can add kinetic energy by heating things up, which is a very easy way. So if we were to use ice or water, because it's a very lowly molecule and it does all three of these phases very easily. You can't see me pointing on the board with my little pointer, so we won't do the works in the beginning of the semester. We will just start up pointing with my finger, because I can do that here. So solid, all your intermolecular forces are going to be pulling and holding everything together. So if you add a little bit of kinetic energy, you can become a liquid. And those things will start to shake and move a little bit more, and then they'll break apart because they're shaking so much. And if you keep those things shaking, and you give them a little more shake, then they can go from liquid, kind of close, to gas, way out here. And they're shaking like the maracas at a swinging party, and they're just going wild. But then you can take away energy, slow things down. Party's getting a little bit slower. Maraca guy's going a little bit slower because in the party he's a little bit drunk, and his maracas are slow. And then the maraca guy gets a little tired. He's starting to slow down. Because you're taking out more and more energy. That'll become solid, and they just sit like this, like you and the pretty lady at the party, just like this at the end. That's how you want to be. So, phase diagrams. They are representations of these intermolecular forces. And you may notice that they are based on temperature and pressure. You may say, Mr. Brock, because I'm not a doctor, Mr. Brock, how come it only shows temperature and pressure when you said physical states are determined on three things: pressure, temperature, and intermolecular forces? Well, I'll tell you, intermolecular forces are constant. So there's no need to graph them because it's the same all the time. So you can see as you increase temperature, down across the bottom, you'll go into more of a gas. As you increase pressure, you'll become more of a solid, sometimes a liquid, but we'll talk about that later. So let's talk about some of the important points in lines on phase diagrams. You can see right here something called the triple point, where all of the lines come in and meet, which at this point, as you can see, solid, liquid, gas, all meet. At this point, if you reach that pressure and temperature, then your substance will be a gas, liquid, and solid all at the same time. So you can have floating ice and boiling water, which is pretty neat to show off to your friends at a party, not like the Moroccan guy, but the triple point. So, and then the lines, what they mean. So the dividing lines will divide whether you're in physical states or not. So when you cross lines, then that will show changes in state. So if you say I'm at 1 atmosphere and I'm going to increase the temperature from let's say 1 atmosphere, and we're going to increase from 0 to, I don't know what this is, probably like 25 seems nice, right here. Then we're going to be melting because we're crossing this line right here, this line, dividing the liquid into solid phases. So you'll melt as you go, back melt or freeze as you go across that line. And then if you go from the liquid to the gas phase, that will be your boiling point line. So at any point on this line will be your boiling point at a given pressure and temperature. And as you go across that line, the liquid will either evaporate and become gas, or it will condense and become a liquid. And then we've got this lovely line down here at the bottom, dividing this solid into gas phases. And that will, crossing that line will either result in sublimation or deposition just depending on if you're going from a solid to a gas, sublimation, gas to a solid, deposition. So let's continue and talk about this lovely little box up in the corner that you may have said, Brock, you skipped that box. No, it's so important that we dedicate a whole slide to it. It's called the critical point. So the critical point of a substance can will vary depending on it, but it's normally at a very high pressure and temperature. And what makes it super critical is not that you memorize where all of them are, because that's not super critical, but that it's between liquid and gas, and it's indistinguishable. So it has properties of both, but it won't fall clearly as a solid, or clearly as a gas, or clearly as a liquid. It will kind of be an in-between state. So it can fuse through solid like a gas, it will pass through. And it can dissolve material like a liquid. So it's very useful in decaffeinating coffee beans, doing your dry cleaning, and much more, which is one thing I always wondered about. When they say dry cleaning, that seems kind of wrong. You're like, how do things get clean when you don't wash them? Because you wash things with water and soap. So I was like, how come my suits are clean? Because it went through the supercritical phase up there, which is a bonus. So if you have a suit, or whatever ladies have dry cleaned, I don't know if you dry clean dresses or shirts, I don't know. But they have probably been at some point in the supercritical for dry clean. Also fun idea. If there are any comic book writers out there, supercritical man would be a bomb character name because it's scientifically factual. But he can fuse through gas solids, like through windows and walls and doors and stuff, and then just punch people and dissolve them, because people are made of salts and dissolve in liquids. So that's a bonus. So reading the phase diagram, we kind of talked about this a little bit, but if you were to come, let's start down here at point B. That's just going to be our initial point on the line. As you go up that line, that will be your sublimation and deposition line. And then at that point where the line bifurcates or branches is going to be your triple point, like the 4 corners, but less cool because it's only 3 corners, and you don't have to stop your car to look at it when you're driving. So it's a bonus. Just pretend it's like Arizona, Nevada, and one other of the 4 corners that I can't remember right now. But that's the triple point. And then as you go up, straight from the triple point, you're going to have this dividing line between solid and liquid. Crossing that line will result in freezing or melting, depending on which direction you're going. And you'll, that's that line. Next, you have this joining line between liquid and gas. And same as before, go from gas to a liquid, condensation, from a liquid to a gas, vaporization. So let us all see how we did on that quiz, on this idea. I will see I click a quiz, and then I click or quiz, and then you all can answer. And we will see how we did. So I'll give that just a couple more seconds here. All right, let's see how we did. A little bit more of a distribution than I would have liked to see, but that's okay, because we will talk about this. So, if I were to travel across this yellow line right here, what phase would I go through? Oh, I didn't write the question. Maybe that's why we missed it. But we'll talk about it either way. If I were to travel across this yellow line, what were the phases that I would go through? Would I, A, go solid, gas, liquid? Let's look. Solid, my line, straight. For it to be solid, gas, liquid, we'll then have to jump down to gas and jump back up to liquid, which it doesn't do because it's straight. So A is not the right answer. So if it were answer C, we would have solid, liquid, gas, or solid, liquid, gas, supercritical, which as we can see, this yellow line does not do. Goes solid, to a liquid to gas and does not shoot up into that supercritical area up in that top corner. So it can't be answer C. So if we were to go for answer D, then it would have to go solid, liquid, supercritical. And we'd run into the same problem as we did in C, as it doesn't shoot up into the right-hand corner. It is not supercritical. That line will never be. So our answer is B. So now let's talk about the solid liquid line and things it can teach us. Solid liquid line is very adequately named, and it is just the line dividing the solid and the liquid, regions, really. And if you look at it, this one is pointing positively, so it's sloping out that direction. If it were to point negatively, shooting back this direction, then we could learn something else. But since it's pointing this way, we can conclude that the solid is more dense than the liquid because its slope is positive. That means if you increase the pressure at a constant temperature, so let's say we have this temperature right here. If we increase the pressure from nothing or negative pressure, whatever it is down here, up and up and up, we're going to become a liquid. And as we keep compressing and pressing, pushing it together, that liquid will get more and more dense under the pressure, and will eventually cross that line and become solid, showing us that the compound or molecule or whatever this is right here has a more dense solid than it does liquid. So let's see how well we understand that concept. Will the solid form of this liquid float or sink in its own, or will the solid form of this molecule float or sink in its own liquid? I'll open that up, see how you do on this clicker quiz. Looks like we have about most of the answers in, so let's see how we did. Excellent job on that one. Good to see those numbers. So the answer to this one actually is B. It will sink. Because if we come over here and we look at this solid liquid line, it's going to slope, and it looks like it starts off pretty straight. So we can't really tell right down here, but as we go up and up and up, it starts to curve out and go to that right-hand corner, showing us that it's a positive slope, meaning that the solid is more dense than the liquid. And if something is more dense, then it won't float. Like ice will have a line pointing from that side up. And I think we have one on the next slide, actually. Yes, this is what we want to talk about, because this is water. So ice, this line points negatively that direction, because ice is less dense than water when the H2O molecules form that lattice structure. So we can conclude that ice would float on water because this line shows that it's less dense, and that is pretty dandy to learn from just a simple diagram and looking at whether it has a positive or negative slope. So a pig in boots. I don't know why the internet does things like this, because a pig already has feet that are waterproof. It's ridiculous. I don't know why. If someone does know why, besides the fact that it's pretty cute, let me know. I was not a pig farmer. I did work with cows though, and I do know hooves are waterproof, and cows are stupid. So, normal boiling point and pressure. If they were to ask a question, say, what's the normal boiling point of this gas? We would look. So normal means it's going to be kind of like standard conditions that you could run into every day. It's never going to be like the conditions on Mars or something. It's going to be Earth, regular conditions. So that would be 1 atmosphere. At 1 atmosphere, if you go straight across this line, the normal boiling point will be at the point the liquid turns to gas, because that's that boiling point line. And as you go from the liquid to a gas, it's going to evaporate, and that's what happens when you boil water. So, at 1 atmosphere, as you go straight across that line, you will then hit the boiling point. And the boiling point is determined by when the vapor pressure it exceeds the atmospheric pressure. So as we talked before, the little Moroccan man shaking his maracas down in the liquid phase. If you press if you press the molecules to shake less, they're going to have to shake more, but they'll shake closer together because they're under that density. And they shake, and then they're still close together, even though if we increase the pressure to up here at 100 degrees where it would normally boil at our standard or our normal boiling point, increase the pressure up here, it's no longer going to boil because you're pressing them into that liquid phase. So then that would cause the increase in your boiling point. That's also why we will see a decrease in boiling point as you go up in altitude and the atmospheric pressure decreases. So, see how well we understood that concept? What is the normal boiling point of this substance? All right, it seems like we've got most of the questions in. So, nice job on this quiz, this clicker quiz. So, let us look and see what the right answer is. The right answer is in fact B, but let's talk about why it is. So A would be 31 degrees. If we were to come over to 31 degree mark and go up 31 degrees, anywhere along here, it's still a gas, 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 gas. Up here, we're going to hit super critical. So, it's not 31 degrees because we're never going to hit the boiling point. And if we were even to have it at like 31 exactly, which would maybe be around here, and we went up, our boiling point would not be at 1 atmosphere because we can look over here and see that that is 5 atmospheres. And this is 73 atmospheres. So up here, it's probably around 70 some odd atmosphere. That's not right. So let's look at C, 1. So 1 is going to be the normal atmosphere for our boiling point, but it's not going to be the temperature at which our substance boils. So 1 would not be the right answer here, because if we go to 1 on our line, it's going to be probably somewhere around here, and then as we go up, that's not our normal boiling point. As we can see, this is 1 atmosphere down here, so 1 is going to be way too high. Is it 78.5? Oh, actually, is it 56.4? B. Let's jump to B. I don't need a fun one to talk about. B, 56.4. We can see that one plotted right here. Comes up, hits our triple point, and then goes over to 5.11 atmospheres. So it's not our normal boiling point because we're at too high of an atmosphere, but it is our triple point. So if we were to achieve this, then we'd have the gas, liquid, and solid all exist at the same time in our container. So, is it 73? No, because 73 would be way on this side. It would be really far that way. So it's not 73, but as you may look, 73 is our pressure for having for hitting the supercritical point. So it's not 73. So that leaves us with one answer of D, 78.5. So if we go to 1 atmosphere, we follow that line all the way over, and we drop down, we'll see that that is 78.5 degrees Celsius. So that would be the normal boiling point of our substance. And with that, I hope this was informative and helpful as you prepare for your test or finals, whatever you're studying phase diagrams for. That is all. I sure hope that was 20 minutes. All the crap that I go through.
The pink slide had nothing to do with what you're talking about. It's just filler. Don't you think they'll know that? They'll be like, he's filling time.
They say 20 minutes, but like
You don't have 20 minutes. to talk
I
about
don't have 20 minutes of material to cover.
Yeah.
I could do a ton of questions, but like phase diagrams are easy. Ooh, stop recording.